All right. Hello, everybody. Welcome to the second day of J Champions Conf, and welcome to this session. All right. Yes, to the second day of Champions Conf, to this amazing talk with Bruno Borges about Java performance tuning on Kubernetes. Really excited to learn all about that. I'm Gunnar. I have the pleasure to host this session here with Bruno. If you have any questions, please put them to the chat. I will take an eye on the questions and I will read them out to Bruno. And I think with that all being out of the way, Bruno, take it away. And I'm going to bring your slides up.
All right, thanks. All right, so hey everyone. I'm Bruno Borges. I work here at Microsoft, and I'm the product manager for Microsoft Build of OpenJDK. I was just joking with Gunnar before if I'm allowed to speak about Java, and yes, it is a fact that I actually use a Mac to present. As you can see here on my screen that is being shared. It is a Mac, and it's such an opportunity, a great opportunity to be here talking to all of you about the secrets of performance tuning Java on Kubernetes. Many of these secrets are actually not big secrets, and this content has been presented before at other conferences, so you've seen it. Feel free to use this opportunity to ask questions, lots of questions. And just drop in the chat and Gunnar will bring them up to me. At Microsoft, what we do is why we have our JDKs, because we have actually over 2.5 million JVMs running inside Microsoft. A lot of those JVMs are used for our big data systems. We use a lot of those Apache projects like Pinot, Kafka, Hadoop, Spark, etc. Flink. We also use that. And there's a lot of projects here that require big data, given the space of AI and everything that we do. If Google is not your main search engine and you use the other search engine, Bing, Bing is powered by Java in the background with a lot of these index powered by Java-based technologies. We use a lot of Elasticsearch as well. And finally, LinkedIn, Minecraft, and even Azure infrastructure rely on Java. So that's why Microsoft is invested in Java, first and foremost. And of course, we also want to help customers on Azure to optimize their Java workloads. So Java on Azure is an important aspect of our investments in Java and open source. Our JDK is currently offered across Windows, Linux, and Mac, and we also build binaries for Intel and ARM and Apple Silicon architectures. And you can get more information about the JDK at microsoft.com/openjdk. So this talk here is about how do we ensure that, number one, we know how the JVM behaves when it comes to memory sizing, CPU sizing, and container awareness capabilities within the JVM, especially when you deploy your application on a Kubernetes environment. And given the way that Kubernetes works with scaling applications very dynamically, horizontal scaling, vertical scaling, and setting the CPU and memory limits and setting the number of replicas, how all of those variables can play an important role at the performance of your application. So we're going to start by looking at what optimizations can be done at the build time and at the startup time of the JVM. And then later on, we're going to look at the ergonomics and the defaults of the JVM, the garbage collectors, and finally, what are the features in Kubernetes that you can take advantage to optimize your application. Performance optimizations don't necessarily mean that your application will perform faster. You may as well be hitting already the fastest response time or throughput in your application for a particular instance, one replica of your application. The question is how you actually make it financially efficient on a cloud infrastructure. If we can get that performance, keep that performance, but reduce cost, that's great. If we can increase the performance and reduce cost, it's even better. So that's what we are looking at. Or you can increase the performance and keep the cost. That's what we are looking at this presentation here. And finally, I have this proposal of what I call the A/B perf test. Instead of doing A/B testing for features, I have this proposal here where you can do A/B performance testing on in production. Okay, so first and foremost, this is not a talk about JVM tuning. There's way more experienced people out there and books that will give you the information that you need to actually tune the JVM to its best for your particular workload. Everything that I'm going to share today here in terms of JVM tuning is a better starting point. If you don't know your application needs, if you don't know the application behavior, everything that I'm going to propose through this talk is just at best a better starting point than the defaults offered by the JVM. And in certain cases, those better starting points may as well be actually worse than the defaults. So you have to keep this in mind and go look for advanced JVM tuning material if you want to go deep into this area. All right, so let's look at size of the container image and startup time. Yes, size is important, but the cost of storing container images and even the cost of downloading those images into a node pool or a VM that runs your containers is not that problematic, especially like in a cloud infrastructure. If your container images are hosted on one data center and your Kubernetes node or VM is on another data center, you might have some issues. But if you do your architecture correctly, you will most likely use the same data center for the container registry and the VM, or at least have replicas of the container registry so that the downloads will be fast. Or even better, you're going to cache those. But if you can go smaller, why not? Security is the main reason for reducing images, not in reducing necessarily the size of the image, but reducing the content inside the image, which most of the time results in a smaller image. It's about reducing the attack surface of your workload. If there is no curl or wget in the command line, a hacker that may get a remote code execution flaw in your workload may not be able to use those external tools to download even more harmful content into your environment. That's an example of why eliminating certain components of the image is important to increase the security of your image. There are different techniques to reduce the image. One of them, and perhaps the most important one, is to use a distroless image. There are many options out there in the market. And at Microsoft, we also offer that. We have a Linux distribution called Azure Linux that has a distroless option. It's not about being small, it's about being secure. And that's what we provide with that distroless image. There are distroless images out there. There are smaller, but the Azure Linux distroless image is a secure one maintained by Microsoft inside Azure. Reducing the Java application, it's also important. You're going to reduce the number of dependencies that rely on. You're going to layer the dependencies in your container image so that when you have to update the container image, you only update the image that contains your business application. And also, if you do this very well, you might as well share a base dependency image for multiple business applications, which will reduce the cost of your storage and also the download if you're deploying two or more applications to the same environment that use the same base layer image that contains all of the dependencies, you are ultimately reducing the size of the download as well. And do run as a non-root user. That's helpful. And finally, the JVM runtime. The JVM runtime is something that many developers have already experienced this, and it does help a lot. The easiest way to have a small runtime is to use a JRE, or a Java Runtime Environment, that some Java vendors still offer. But Java is moving towards a place where there's no JRE anymore. It's all about having the JVM and the components of the JDK that are required for running a Java application. And the way you do that is using a tool called JLink. So the JLink tool in the JDK creates a custom Java runtime tailored specifically for your application needs. You won't have the Java compiler, you won't have a Java debugger or anything like that. It's just a Java runtime with only the APIs that are needed by your application. If you want to go the extra mile and have a native image, you can use Growl VM, Substrate VM to create a native, truly native binary of your application, which gives you great startup time and also smaller binaries. So here's just an example of how images can get reduced. Like if you look at Debian, there's 117 meg for a Debian image-based image. Ubuntu has 78. Then you can go to the Debian Slim, 74, and then Alpine with Muzzle libc, 7.8 megabytes. We don't necessarily recommend using Alpine for production environments unless you know and you're experienced with Alpine, then that's fine. But on Azure, what we do is we recommend the use of Azure Linux in our supported images, because that's part of the commercial support agreement. Different vendors will have different support agreements as well in terms of like what images can be used. In Azure, you can use any image for almost every service, but you get commercial support if you use certain recommended images. Here's an example of a Spring application and how this gets optimized. So we get the JDK, we get Alpine, we get the jar file, which is a fat jar file, and then the entry point is Java minus jar. One way that you can start optimizing this thing is, again, you don't run as root, you run as an app user. The other thing is you use layers to copy your dependencies. So only the application code will be updated later on. And you might as well extract that into another base image if you want to, if you're thinking about sharing the dependency layer with other business applications. One thing that lots of developers do is they use the Spring Boot Maven plugin, which by default will actually build your container image using a technology called build packs. Build packs are a build pack for Java is a great technology that optimizes your container image already for container environments. Some of the recommendations that I provide here are actually already implemented in that. So if this is the way that you're building your Spring container images, you're already getting the best of everything in terms of best practices for reducing the size of your image and optimizing your JVM for containers. If you're not doing this, or you want to stop using this because you don't want to depend on the build pack, then let's continue this conversation so you can learn some of the things that happen behind the scenes and what things you can do by yourself to achieve similar results. Here we talk about the JVM runtime. Okay, so the full JDK is around 300 megabytes. But once you have a J-linked custom Java runtime, you can get as down as 60 megabytes for your Spring application. And if you go to the Growl VM native image, it's even smaller than that. Another technique that can be used to improve your application startup time is class data sharing. This feature is available in the JDK for many years now, and not everyone is taking advantage of this. But what this does is basically optimizes all the jars and everything that is used by your Java application into a binary archive that is mapped to the platform that you're going to run. So imagine like a jar file that gets prepared for a Windows environment or a Linux environment for that particular JDK. And it loads faster in the memory, which gives you the faster startup time. There are future projects in this space to improve startup time. One is Project Layden by Oracle, and the other one is Project Crack by Azul System. Both projects have similar goals: improve the startup time and warm-up time. Startup time is the time that the JVM takes to the JVM and your application takes to start, and warm-up time is the time that it takes to hit peak performance to some degree. And both Layden and Crack aim at improving not only startup time, but also warm-up time. Think of it this way. If you're going to scale an application horizontally and you need that responsiveness as fast as possible, what you truly want is improved warm-up time. Having new replicas being created as fast as possible is great, but if the JVM is not at a good warm-up time state, you don't get that true performance. So that's why these projects are extremely important. Here are some benchmarks from the Layden project. You can see how it gets extremely fast compared to the default without Layden in JDK 22. Lots of different benchmarks here. Just by enabling class data sharing, here's application class data sharing for Spring, for the Spring application, you see how it dropped at least like 30% of the time for this application. So there's lots of benefits, and you should definitely leverage all these capabilities. For Project Crack from Azul System, this is like the sort of performance that you can see when implemented well in your application. On a Spring Boot application, it went from 3.8 seconds to 38 milliseconds. That's a lot of performance gains. Same benefits for Micronaut, Quarkus, or an XML transform benchmark. So to summarize, optimize your container image, optimize your JVM, and optimize the startup time in many different ways. And if you really want to go the next level, optimize the warm-up time with projects like Layden, Crack, and others that are currently in development, currently in research, but some of these are already available for you to actually run. Crack has a production level build that you can try, but of course we always encourage customers and users to test as much as possible. So let's go and understand a little bit of the JVM defaults and why understanding the JVM defaults is important. Remember that Docker file that I showed before with java -jar? That basically means when you do java -jar, your application jar file, you're going to rely on the defaults of the JVM. If you're not setting heap size, if you're not selecting a garbage collector, if you're not setting the number of threads for the garbage collector, if you're not setting the thresholds for collection time, and etc., the JVM will come with the defaults.
Hey, Bruno.
Yeah.
Before you go on, there's one question from Vincent, and it's pretty open-ended. So what do you think of native images?
What do I think of native images?
Yes.
I have not run myself a native image in production yet, but I imagine that one of the main challenges of the native image, I mean, the benefits are clear, lots of benefits. So when people ask me what I think it's great, but let's talk about the challenges. And the main challenge to me is debugging. Debugging a native image is challenging, especially if you have a Java-based version of the application on your testing environment, and then you do a native image, you run some tests, and everything works, and then you deploy in production. But then the problem happens in production. Debugging that back into your testing environment is a little bit difficult. Not impossible. And I believe GraalVM team from Oracle has recently added debugging capabilities into native image. I don't know what is the latest state of that, but that was one of my concerns in the past. Maybe now it should no longer be a concern.
Yeah, I think some progress has been made also from the Red Hat guys, but I agree. I think it can be challenging.
Yeah, exactly. So in general, it's a great technology, and it should be considered by everyone when performance needs are critical.
Awesome. Thank you so much.
Yep. Okay, so going back to the JVM defaults, we call these default ergonomics. And I like to say that in the case of the JVM, there is always premature optimization. Those defaults are, to some degree, premature optimization. Think of it this way. You are not setting the heap size, but someone is setting the heap size, or something is setting the heap size. And that heap size being set is by the default ergonomics, or the values that the JVM believe are good enough for your application in a particular environment with a particular amount of memory. But that is premature optimization. If I set the heap size to 70% of the memory, is that premature optimization? Well, maybe. If I set to 50%, is that premature optimization? Maybe. If I don't know. If I have never run the application myself, I just built the application, but I'm gonna push to production. I did functional testing, everything works. I'm gonna put it in production, and I'm gonna set the heap size to, let's say, 50%. Is that premature optimization? Some may say yes. You don't know what the application needs. Well, I don't. But guess what? 50% is what the JVM sets as default as well in certain cases. In other cases, it sets a default of 25%. But the JVM doesn't know what your application needs. Those are conservative values that will get your application to work in most cases, in most environments. So it's a guess. It's a conservative guess, and that's okay. But in my opinion, it is a premature optimization nonetheless. Defaults are premature optimization as well. So that's my opinion. But we can have, of course, a debate on this. And the important thing, though, is if you're going to benchmark an application, you have to have a baseline. And the baseline tends to be the default values at the very first test. You test your application with default values, and then you start optimizing. It can get worse. It can get better. So that's your baseline. So everything is premature optimization. But what there is a baseline for your performance test. And that's what the defaults actually mean. So let's do a quick puzzle here. We have this application here, and this application will show how many processors are running in the environment. And I'm going to run this application with this Docker command. I'm going to set 2 processors, and I'm going to set 1,500 megabytes of memory. And I'm using JDK 17 in this particular case. So the question I have for you is, and I'll give you 30 seconds to respond in the chat. What will be the garbage collector selected? That's the question number 1 for this puzzle. What will be the garbage collector for this application? 2 processors with 1,500 megabytes. So the options are serial garbage collector, parallel garbage collector, G1 GC garbage collector. There are other GCs in the JVM, but just keep those 3 in mind: serial, parallel, and G1 GC. Which one do you think will be selected by the JVM in this particular case?
So 2 people saying G1 so far, 3 people.
Okay. And that's because people probably heard that the G1 GC is the default GC in the JVM these days. Well, the answer is serial GC. In this case, serial GC will be selected by the JDK, by the JVM. You see here that serial GC is true, parallel is false, Shenandoah is false, G1 GC is false, ZGC is false. And you can see on the right side, ergonomic, because this was ergonomically selected by the JVM default algorithm. Okay, so even though you have two CPUs, the amount of memory in the environment is not enough for the JVM to believe that it can use G1 GC. That is the tricky point here. Okay. Okay, so this is the actual algorithm inside the JVM today for all versions. Even JDK 22, JDK 23, it doesn't really matter, early access. This has not changed since ever. If the environment, the whole environment, has that available memory, which is the x-axis, the JVM will set the heap size to those values by default. And there is one very confusing flag here called mean RAM percentage and max RAM percentage. The mean RAM percentage is actually the heap size for when you have a minimalistic environment, like an environment that has no more than 256 megabytes of RAM. The max RAM percentage sets what is the heap size when the environment has more than 512 megabytes of RAM. So if you're setting max RAM percentage to 70%, but you give an environment with less than 256, you don't get 70%, you get 50 by default. And anywhere between 256 and about 512 megabytes of environment memory available, you get pretty much the same amount of heap, 127 megabytes. So this is how important understanding the default ergonomics of the JVM helps you adjust your application. And I know many developers use max RAM percentage now, especially in container environments. But then when they go the route of setting even less and less memory, they actually end up with the 50% by default. And why those values? Those values exist from a time where servers were shared. In the year 2000, servers were shared for many different types of workloads. You had your JVM workload, you had your shell daemon process to access your environment remotely. You had your Apache web server, you had a Samba server for file system sharing, you had a relational database, all of that shared in the same environment. This was actually common back in the days. You had these big machines and everything was shoved into those machines. But then after around 2018, we saw the explosion of Kubernetes and container adoption. And now environments are dedicated. Environments tend to be dedicated now for a single workload, especially in container environments. So what we see now is an opportunity to set new default ergonomics for the JVM. What those numbers can be, we don't know yet. There's a lot of research, there is a lot of testing that needs to be done to change these values, if at all. I mean, we may not actually ever see a change here. Maybe we see enhancements in other areas. But clearly, the behavior changed from shared environment to dedicated environments, like even dedicated VMs, small VMs, but still dedicated VMs, and not just containers. And also in IoT space, we also see that happening sometimes, where you have a dedicated hardware for one particular workload. So the main lesson here is do not just Java manage your application. You have to understand the defaults so you know what will be selected by the JVM. Ideally, set the values yourself. Set the heap size, set which GC you want to use, set other parameters if you know what they mean and what what behavior it will drive in your workload. But we have quizzes where we ask people, do you know what garbage collector is running right now in production? People don't know, and they sometimes when they guess it wrong. So use this as a warning to check your production environment, that not only you're setting appropriate heap size, you are using the appropriate garbage collector, and your application is not wasting resources. Because the most important thing here is, if you're especially in the cloud environment, what you don't want is to waste resources. I mean, cloud vendors like Microsoft Azure, we love customers using lots of memory and lots of CPUs, but we want customers to use what they need. If they don't need 2 terabytes of RAM, don't use 2 terabytes of RAM. Use what your application needs. Use what is reasonable to your workload performance needs. So let's talk about garbage collectors. There are different implementations, as we saw briefly in that quiz: Serial, Parallel, G1, ZGC, Shenandoah. There are a few others available. One of them is Epson GC, which is a no operation garbage collector, which is great for benchmarking to some degree, or testing your application, or testing the JVM actually. But the important thing here is each garbage collector is its own implementation, and they may have different data structure needs. By having different data structure needs, it means that the memory consumed by those garbage collectors outside the heap size. Remember, the heap size is the area where your application objects live. But there is what we call the off-heap or non-heap memory, or off-heap memory, where everything that is not heap is also being used by the JVM or by native libraries that your application may be integrating with. Anything that is outside heap will be here, including the data structures used by your garbage collector. This heap is what we usually set, 70%, 50%, whatever. The non-heap, we don't set. There are certain areas of the non-heap that we can set some limits, like code caching, meta space, and yeah, those are two that I can remember right now, but there might be others. These usually you don't actually set a limit. It may grow and shrink very fast throughout the execution of your application. That's why those conservative numbers, 25%, 50%, and even why we don't set heap size to 100% ever. No one should set a heap size to 100%, because if you're using 100% of the memory of your environment just for the heap, where are you going to allocate the non-heap memory, right? So you need that. And there are some research in how to make this more manageable. How can we track this memory consumption, and how to set some limits as well to areas that today don't have a limit, and what to do when those limits are reached. So there's a lot of research in this space, but right now the situation is you have to be aware of heap size and non-heap size, where memory is used by the GC to store data structures needed by the GC algorithm itself. So what happens with this native memory usage or off-heap space? So here we have two images here on the left side and the right side. One we call the JVM.large. Consider this a VM, not just a container. I mean, you can consider a container, but it's an environment. And then you deploy a Java application with, let's say, consuming 70% of memory. Okay. And then the heap scales, right? Because it's 70%. So the more memory you give to the environment, the bigger will be the heap. But the interesting thing here is the non-heap usage by this application is actually that amount. And the interesting thing here is, even if you split this deployment into two replicas, into two copies, and have two smaller VMs or two smaller containers, the non-heap area will not be significantly smaller. It will be the same size, at least around the same size of a larger environment, that space. Of course, this is I'm making a very generic statement. There will be workloads that this will not match, but for many Java web applications, REST API web applications, this is roughly what happens in most cases. The non-heap consumption is kind of the same, whether the JVM is the heap size is big or small. So this is where we can start seeing some opportunities to optimize either the performance or the cost or both. So yes, we do suggest that container environment or dedicated VMs use heap size around 70, 75%, something around that space. You can use the max RAM percentage, again, when the value of the environment has more than 256 megabytes of RAM. Otherwise, you have to use the mean RAM percentage. It's very confusing, but it is what it is. And you have to watch out. Don't set a very high percentage here ever, or otherwise native off-heap memory will be used, and it may kill your container because of that. So that's where you get OOM kills on Kubernetes. So I mentioned build pack before, and this is basically what build pack does for you. It will set the heap size based on some calculation. It will get the total container memory and subtract what the calculator believes the non-heap needs are. And the non-heap needs are equal, you can see below, to direct memory, which is an estimate, plus the cost of the meta space, which is the metadata of your application, the jar files, the classes, etc., plus a reserved code cache, plus the number of threads times the stack size of the threads. So that is your non-heap cost, roughly. So this software here, the Paketo build pack, which is used by Spring by default, will do this calculation for you and return a heap size that is more reasonable to set to your container environment. So if you're not using Paketo build pack, you should consider using it. If you're afraid of depending on it because you don't know what these values may be, and you want to have as few dependencies as possible on third-party software in your production environment, then you might as well do these things manually by yourself. So the interesting thing here is that the non-heap calculation of Paketo build pack actually relies mostly on the defaults of the JVM, no matter what. The only thing that is actually calculated is the meta space size, which is, and also the thread stack is different for Tomcat workloads. But the reserved code cache and the direct memory, those are defaults as per the JVM. But you can tweak them if you want. All right, so let's talk about Kubernetes. Kubernetes has many scaling options. One of them is the vertical auto-scaling. Actually, the title of the slide is wrong. There are different types of auto-scaling Kubernetes. One of them is called the horizontal pod auto-scaler, and the other one is vertical pod auto-scaler. The horizontal, it's the most common one, just gives you more replicas. I have, let's say, 2 replicas, and I see a performance issue. I can just go and do a horizontal pod auto-scaler. And now I have 10 replicas. Now I have 50 replicas running on my cluster. So there is actually a story about this one where there was a company in Latin America that complained that Java was not performing well. And they said, we're gonna rewrite our code in Rust because the JVM is consuming too much memory. The performance is not good. We have hundreds of replicas and it's still not enough. So I checked with them, and they actually were deploying one CPU limit containers with, 500 meg or 1 gig of RAM for those containers. And they had dozens, like 50 replicas for one single application. That's not how auto-scaling should be used. It should be used to scale peak hours. But your average should not have that many replicas. So consider this. You identify your application runs well with X amount of CPU, X amount of memory. And then you see that, you know what, I don't have a node with 50 gigabytes of RAM, but my application works well with 50 gigabytes of RAM. Well, in that case, it's reasonable to have 2 replicas of 25 gigabytes of RAM, or even 3 replicas of 20 gigabytes of RAM for each. So you have 60 gigabytes around. The horizontal pod outscaler is for unpredicted needs or peak needs that are way outside what you usually see, and that's when you do that. But if your goal is to have dozens, hundreds of replicas at all times, you should reconsider that, and that's what these next slides will help you with. The vertical pod outscaler is great because it does exactly that. It increases the amount of CPU and or memory to your JVM, but there are some, of course, limitations to how this can be applicable, especially in the case of the JVM. There is a new feature in Kubernetes called in-place pod vertical scaling, which will increase either CPU or memory, but the JVM today does not refresh some of that data once it's up and running. So the JVM would need to be a little bit smarter. Some other workloads are fine, but not the JVM at this stage. So here's another project also, which is the startup CPU boost. The boost of this project is, hey, run my application with 3 CPUs for the first 60 seconds. And after that, reduce the amount of CPU or reduce the limit of CPU. That's a great feature because a lot of CPU usage happens at startup time by the JVM. It will consume a lot of CPU. It needs to read a lot of files. It needs to create data structures. It needs to do a lot of things at that stage. So having a CPU boost at the beginning will help with your startup time. So this is a great feature to consider in your production environment. All right, so Java and Kubernetes. When we set a CPU limit, we are not setting how many CPUs we have access to in the JVM. We set how much CPU time we have access to, and for during a particular CPU period. So if I say 1,000 millicores, that does not mean a single CPU will be available to the JVM. It means that the time 1,000 millicores will be available to the process. 1,000 millicores may as well be split across 2 CPUs in parallel. 500 millicores running here, 500 millicores running here. Java applications are, in general, multi-threaded, whether you have current GC up and running, whether you have a web application with threads on Tomcat or Jetty or whatever server container you are running. Database connection pools also have to maintain their own threads. Every thread on that is running parallel, but by nature. So if your application is a Spring app, you're going to have multi-threads inside. Luckily, the JVM manages that for you. But the reality is, in a 1,000 millicore, which on average lasts 100 milliseconds, that's the CPU period on Kubernetes, those 1,000 millicores will be consumed faster than the 100 millisecond period for that CPU. So how do we visualize that? Here's an application running. You have the Java virtual machine running on a node with 4 CPUs. This application, this container, has a CPU limit of 1,000 millicore. And the CFS, the CPU period for this is 100 milliseconds. Okay, so my application receives 4 HTTP requests at the same time. Each request gets processed by the 4 CPUs at the same time. And let's assume that each request consumed 200 millicores of CPU time. Well, 4 times 200 millicores, that equals to 800 millicores. But my CPU limit was 1,000 millicore. Well, now I only have 200 millicores left. But that execution of the 4 HTTP requests took only 20 milliseconds to be executed. The CPU period is still going, and I now have left 80 milliseconds of CPU period time. Well, of CPU period. Well, what happens now is the garbage collector, after those 4 requests, had to run to clean up some dirty objects and some trash. It ran in parallel. Each GC thread, one thread cleaned up this heap area, the other thread cleaned up this other heap area. Whatever happened, those GC threads had a total cost of 200 millicores. And now my CPU period has still left 60 milliseconds. What will happen now if another request comes in is it will be throttled. And that's what happens in production when you see application being throttled. The application, the workload consumed all of that CPU time, the CPU limit, faster than the CPU period, which means your application is not allowed to use CPUs anymore until the next cycle. So you have the application here will be throttled. So those 2 requests, they will have a latency of at least 60 milliseconds. So the latency of those HTTP requests will go from 20 milliseconds, which was the time that they took before. Now they're going to go to 80 milliseconds because it's 20 plus the 60 milliseconds of throttling. And that's where you see those jumps in latency on your Kubernetes-based workloads. So another thing that you can consider is actually, okay, you know what? When the JVM starts, it will reach the CPU limit. If that limit is 1,000 millicore, the CPU understands you have 1 processor. If it has anywhere between 1,001 millicores and 2,000 millicores, it understands it has access to 2 processors, and so on and so forth. But this does not mean that threads will not run in parallel, like more than 2 procs. Like I demonstrated before, it might as well run 4 threads at the same time. The only thing that this does is we'll adjust the JVM, and any library that reads this information, the active processor count, will adjust thread pools. Thread pools will be based mainly on the number of processor available seen by the JVM, however the JVM counts them. What you can do is trick the JVM. You can set a 2,000 millicore CPU limit and tell the JVM, you know what? The active processor count is actually 4. You can do that. Where this can be beneficial, it really depends, but it is something to be considered. We did this map a while ago, and we probably have to revisit again. But this is what we believe is a better starting point for your workload, especially when you don't need especially when you don't know what your workload needs. If you're setting a CPU limit of 1,000 millicore, do an active processor count equals 2. Because in many cases, you're going to have a lot of IO-bound activities in web applications. And when you have IO-bound, you're just like waiting for IO to happen. You might as well do some work done at the CPU in the meantime. So that's where maybe increasing the processor count to 2 in that particular case may be helpful. What we do recommend is the green bandwidth here. We do recommend the use of 2,000 millicore or even 4,000 millicore with parallel GC or G1 GC. And then how much memory you set as container limit and how much heap size you set at 75%. So let's talk about resource redistribution. This is a benchmark that I did a while ago, but it shows basically the idea that more replicas don't necessarily mean better performance. What you see as the green line here for the latency chart is 6 replicas of 1 CPU container. So I got 6 containers, each with 1 CPU, a total of 6 CPUs. Then I redistributed my workload, and I deployed 2 containers with 3 CPUs each, still a total of 6 CPUs. That is the red bar for throughput and red line for latency. You can see how much throughput I increased and how the latency dropped to nearly zero at the 99.9999 percentile. I basically kept the same cost, but improved the performance. The orange line and the orange bar shows 3 containers with 2 CPUs. I still am consuming the same amount of resources, same amount of memory, same amount of CPU, and I increased my throughput slightly, just very slightly. If you look closely, the orange bar is just slightly above the red one, but at the cost of latency. Latency got slower in here. So what can I do here now to test this environment? I can actually go back to 2 containers and reduce the amount of CPU. So I went back from orange, I went back to red, 2 containers, but instead of 3 CPUs, I did 2 CPUs. You can see that the bar is now slightly below the red, but way above green. And the blue line for latency is slightly above orange, but way below green. 2 containers times 2 CPUs is 4 CPUs. That is 2 CPUs less than 6 that I had before. So in here, I achieved 2 results. I improved performance and reduced cost. If you can do tests that validate this redistribution, you can find cost savings and performance improvements at the same time by just redistributing the resources more evenly across your JVM. Because the JVM needs CPU, the JVM needs memory, and having more replica won't necessarily scale your performance at the same rate. So this chart is perhaps the most important one in this presentation, so you can understand the possibilities and the opportunities to improve performance and reduce cost. To give you an idea, this is a cluster on Kubernetes. The estimated cost for this is $840. I think it's per month, but it doesn't matter how per month or per day. There's a cost, and it's $840. And you can see that I have 3 replicas per VM, 3 JVM replicas per VM. The control container is a control container of the Kubernetes environment. So you cannot actually take that resource away. Now, what I'm going to do is I'm going to merge pods. Instead of having 3 pods of the same application per node, I'm going to have a single pod for that application on that node. Now I went from 1 CPU to 3 CPUs. And I reduced the number of replicas as well, but I'm basically running 1 replica on an entire VM. Well, what else I can do? I can continue merging the pods. So now I have 6 JVM replicas instead of 18. I'm still consuming the same amount of memory and the same amount of CPU total, but the cost is still the same. And I very much improved the performance here for this workload. Assuming I had performance issues, I may as well achieve the better performance just by rearranging the resources. Well, what else can I do? I can actually reduce the number of VMs and increase even more the amount of CPU and memory for each replica. So now I'm running only 3 JVMs, 3 replicas, with 8 CPUs each. I'm still paying the same amount of money for this environment, which is these 3 VMs of 8 CPU each. But the thing is, if this is giving me the same performance as before, I have now achieved efficiency. I'm running the same performance, but at lower cost. Well, we are still paying $840, so it's not exactly cost savings. It is cost savings because now I have this amount of resources available to deploy other containers. So I have 9 CPUs, 9 vCPUs available, 9,000 millicores available to deploy other workloads. That is cost saving. So this application, the Java application, reduced its cost. So how do you identify these opportunities? So I have this idea of A/B performance testing. So basically, you deploy the same workload with different topologies on Kubernetes, and using some smart load balancing, you can do that in production. Again, this is not necessarily about this is not about functional requirements. This is about non-functional requirements, about performance testing in production. So you have your load balancer getting all the requests, and then you have two services on Kubernetes. One service on Kubernetes is for your application with smaller JVMs and multiple replicas. And then you have another service instance that has behind it has larger JVMs with fewer replicas or lesser replicas. The main load balancer will just route all the resources here. So here you can actually start adjusting, and let's say topology A, topology B, and even topology C, where you reduce the total amount of resources being consumed by that topology. And that's what will give you the idea of which distribution of resources is more efficient for your workload in production. Here's an example of how this works, and I have a source code available on my GitHub. But basically, you have this Nginx running, and then there is an HTTP backend, and then I have the sample application deployed on a 2x2 containers. So it's two containers, two replicas by 2 CPUs. And then I have this other one is 2 replicas by 3 CPU, 3 replicas by 2 CPUs, and 6 replicas by 1 CPU. And then, of course, I have in this opportunity, I can also do an A/B performance testing of garbage collectors. So if I can test the distribution of resources, I can also test JVM tuning configuration. I can have the default ergonomics, or I can have my application with G1 GC, or I can have my application with parallel GC, or I can have my application with this JVM tuning settings and that JVM tuning settings, and I can measure which one is performing well. So how do you track this to actually see the data? Well, for each configuration here, for example, sample app dash ergonomics, you're gonna have a monitor profile. So let's say you're using New Relic or Datadog or Azure App Insights, you're gonna actually configure a profile for that topology. And then once you go to your dashboard, you can select each topology and see the metrics for each of those deployments. Again, the application is the same, but everything that is non-functional about it is different. And that's where you can do those tasks in production thanks to Kubernetes. So what have you learned? Container images, yeah, make it smaller, but think about security first and foremost. Startup time, you can optimize today, move to Graal VM if needed. JVM tuning, understand the defaults, configure the GC and the memory based on constant observability. There are some better starting points than the defaults, but they are not silver bullet. They might actually make your performance perform worse than the defaults. Use the defaults as a baseline and then adjust from there. Understand the impact of resource distribution and resource constraints on Kubernetes, because the JVM has certain needs that cannot be minimized. The JVM is its own process. Your application runs on top of the JVM. If the JVM needs 800 millicores of CPU to perform well, that's what it will need, aside from the application needs. And then use A/B performance testing to validate different topologies for non-functional requirements. If you want to learn more about Java at Microsoft, go to developer.microsoft.com/Java. If you want to connect with me, I'm on Blue Sky, I'm on Twitter, X, I'm on LinkedIn, I'm on, I was going to say Pinterest, but no, I'm not on Pinterest. Yeah, I mean, this is what it looks like when you do a perf test. So here I have a Kubernetes running with a Java application, and I'm going to perform this test. I'm going to do 12 threads with 400 connections. And what I deployed here was, I think, was 6x1. Yes, and it's here. Here you see this application insights role name. That's 6x1. So when you go to the dashboard, you can actually see the role here, 6x1. So that's my topology. If I deploy a new topology and I change that value, I'm going to have another service with a different topology, and I can select here and compare the different topologies in real time. So this is just to show you how it works doing A/B performance testing in production. All right, that is all that I had. Thank you very much.
Awesome. Bruno, thank you so much. I don't see any more questions right now. So if people have last questions, this is your opportunity. Some people gave you praise in the chat. I put those remarks up, so people really liked the presentation you did. Great job. Martijn, I'm not 100% sure what's the context there. He's saying you should check your Mastodon feed. So maybe Satya has been giving you a pay raise over Mastodon and you should go there and check it out. I don't know. Other than that, I know. Bruno, any last comments?
No, just don't do Java minus jar. That's number one rule.
Yes, that's the main takeaway. Awesome. Then, well, thank you, Bruno, so much for presenting. Thanks to everybody for being here. There will be more amazing talks today and then also on Monday and Tuesday next week. So you definitely should check those out. And with that, enjoy very much the rest of Champions Conf. Bye-bye.
Thank you.